Hello and welcome to the second part of Lesson 6. The last part of this lesson concluded with a workflow that could be used to help us solve a heat transfer problem. An essential part of solving these problems is to have a solid understanding of the various heat transfer mechanisms that dominate the problem right from the outset. This can lead to simplification of what could be quite a complex looking problem to one that may be quite simple. One of the tools that we can use to aid understanding and problem simplification is dimensional analysis. In particular, there are 5 non-dimensional groups that I would like to remind you of, all of which are useful when it comes to quantifying heat transfer problems. So, let's see how these groups can fit into the workflow that we've discussed and how these groups can help us to build that initial mental model that is so important at the outset of the problem-solving process. So, in the last part of this lesson, we introduced this workflow here. Draw a diagram, identify the modes of heat transfer, as I said, sit down and think about it, and then simplify the problem. Is it 1D or 2D? Choose coordinate systems, identify boundary conditions, and so on and so forth. Now, non-dimensional groups and dimensional analysis can help us in that second step. Have we got a one-dimensional problem or a multi-dimensional problem? It can also assist us in this final step. I've got a convection boundary condition. How can I get an estimate for my heat transfer coefficient? Okay, it can also help us right at the outset when we're thinking about modes of heat transfer as well. So let's have a look at these 5 non-dimensional groups. In particular, what I want to focus on is what they mean, because it's very easy to get lost in the equation of a non-dimensional group. Or is it rho Cp over K? I've kind of forgotten what a Prandtl number is. What's really important is understanding what those numbers mean, and then what meaning and information we can glean from them such that we can expect to predict mentally what that answer is likely to look like right at the outset. So let's start by thinking about the number of dimensions in the heat transfer problem. By this, what I mean is, have we essentially got just a temperature gradient in one direction? Brilliant, 1D problem, analytical solution. Or have we got a temperature gradient in multiple different directions? Not to say you can't get an analytical solution for it, but the maths for that's a bit more involved, or we more likely are going to have to resort to a numerical solution, which takes a lot more time. And there's a lot of scope to get numerics wrong. So let's think first of all about the physical shape of what we're dealing with. If we're dealing with fibre spinning, what does a fibre look like? It's a few hundred microns in diameter and a few meters long. Well, the chances are the dominant gradient in that is going to be along the length of the fibre. Unless you've got an exceptionally poorly conducting material and exceptionally poor heat transfer conditions at the surface, there's unlikely to be a gradient in the radial direction. However, we can contrast that with extruding a great big pipe. Same cylindrical geometry, but let's say we've got a, 10 centimetre diameter pipe, and we're looking at a ½ metre length. Well, actually, that's quite a chunky aspect ratio. It's not implausible to think that the core of that pipe or the core of that rod could still be quite hot even when the surface is cold. So have a look at what you're dealing with to start with. If you've got a long, thin geometry, you're more likely to be looking at a one-dimensional problem. If you've got a short, fat geometry, you're probably looking at a multi-dimensional problem. So the geometry can give us a very big clue as to what to expect. If we want to formalize this, then there's a non-dimensional group that we can use to help us called the Biot number, named after Jean-Baptiste Biot, who was a Frenchman, and he was a heat transfer person who lived a very long time ago, but he pioneered the use of a ratio. And this ratio is very simple. It's the rate of heat transfer by external convection divided by the rate of heat transfer by internal conduction. And we can simply write it as H, the heat transfer coefficient, times L, my surface to volume area ratio, which has units of meters, divided by K, my thermal conductivity. So let's think what this actually means for us. Let's draw a diagram. So that blue box on the board is my solid. The blue arrows are the heat transfer by conduction, and the gold-shaped arrows are representing the heat transfer by external convection. Note the word external, that's really important. So let's have a think about the competition between these two processes. Now, if conduction dominates a problem, well, what might make conduction dominate a problem? If I've got a high thermal conductivity, if this is a metal, let's say, then conduction is going to happen quickly. Which means that if there's a temperature imbalance, the energy flow to equilibrate that is going to be fast. If that happens faster than heat can leave the surface, by convection, then in that direction of conduction, in the direction of the blue arrows on the board, there's unlikely to be a temperature gradient, or a significant temperature gradient at least, because the rate of heat removal at the surface with the gold arrows is slow compared to how quickly heat can conduct within the material with those blue arrows. And so in the direction of those blue arrows, there's unlikely to be a gradient. The gradient may well be perpendicular to those. Let's reverse the scenario. Let's think about a material now that has very poor thermal properties. Polypropylene, for example, 0.172 watt per meter per Kelvin thermal conductivity. So, if we've got a large thickness of polypropylene, the rate of heat conduction is likely to be quite slow because it's a poor conductor of heat. If we've got forced convection at the surface, we've got, I don't know, an air quench or a quench tank, then the rate of possible heat release there is quite quick. And so what we have is heat removal from the surface quickly, driving a temperature gradient through the material because heat transfer within the material is really slow. So these lead to two different values of the Biot number. If internal conduction is fast, i.e. with our metal, the denominator is larger than the numerator, the Biot number is less than 1. If the Biot number is less than 1, you know that's a pretty good indicator that you've only got a temperature gradient perpendicular to the convection direction. It's a 1D problem because heat transfer by conduction is quick. If the Biot number is greater than 1, that infers that the rate of external convection is faster and greater than the rate of internal conduction. Therefore, you're likely to have a temperature gradient in that convection direction, as well as probably perpendicular to it. So you've probably got a 2D problem. So, in summary, the Biot number is really useful in helping us to assess whether we've got an essentially one-dimensional heat transfer problem or a multi-dimensional heat transfer problem. Now, we also said that dimensional analysis can help us get data. In particular, it can help us obtain values of heat transfer coefficients that we can use to solve convection problems. So let's look at that in a little bit more detail. The essential non-dimensional number here is the Nusselt number. Now, when we use the Nusselt number, we've got to be a bit careful, because if we look at how it's written, Nusselt number equals HL over K. And it's a total rate of heat transfer divided by a conduction heat transfer. It looks very, very similar to the Biot number. In fact, I've known people to accidentally interchange the Biot and Nusselt numbers. But the Nusselt number is all about the contribution of convection to a problem. So let's look at it in a bit more detail. We're dealing with the outside surface of that film, of this polymer film. So the numerator of the Nusselt number is the total rate of external heat transfer. It's the conduction contribution and the convection contribution. Because if we've got a hot polymer film sitting in air, don't forget that it's perfectly possible for that air to also conduct heat. The dominant mechanism is going to be convection based because of the buoyancy of the air changing as a function of temperature, but both heat transfer mechanisms are possible. The denominator of the Nusselt number is simply the rate of heat transfer by external conduction, which is our base case. If there's no convection, the only heat transfer mechanism is by conduction. And so you've effectively got the denominator and the numerator of the Nusselt number being the same thing. It's the rate of heat transfer by conduction divided by the rate of heat transfer by conduction. Therefore, the Nusselt number is 1. So the lower bound of your Nusselt number is always 1. So your Nusselt number is always greater than or equal to 1. Okay, and we'll see in future parts of this lesson there are many correlations that we can use depending on the geometry of the scenario that we're looking at that gives us a value of the Nusselt number, which in turn we can use to get a value of H, that heat transfer coefficient for convection. So, a lot of Nusselt number problems all depend on the length scale of the geometry. We'll talk a lot more about that in future parts of this lesson. And we'll also look at 3 or 4 key Nusselt number correlations that allow us to estimate values of heat transfer coefficient. Okay, so remaining on that subject, if we're going to be looking at Nusselt number correlations later in this lesson, we need to look at the non-dimensional groups that they involve. And if you look at Nusselt number correlations, you'll often see the Reynolds number appearing. Now, I'm sure you're all familiar with the Reynolds number, since we've already done the fluid mechanicsy part of this course. But just as a reminder, for a Newtonian fluid, the Reynolds number is the rho times d times v over mu. But as I said at the outset, let's not get too wrapped up in the equation. Let's remind ourselves what it's telling us physically. It's the inertial forces divided by the viscous forces. So it is a measure, in a sense, of how much momentum there is in a problem and whether momentum dominates or not. Low Reynolds numbers are non-inertial, negligible momentum. High Reynolds numbers tend to be inertial dominated. And remember that we can also use a Reynolds number to determine whether we've got a laminar flow scenario or a turbulent flow scenario. Remember also that the Reynolds number will take a different form for generalized Newtonian fluids. We've seen in previous parts of this course the Reynolds number as written for, say, a power law fluid. So be careful that you're using the correct Reynolds number. If we're thinking about natural convection correlations or forced convection correlations, you'll also see the Prandtl number, named after Ludwig Prandtl, who was active around the turn of the 1900s. And this is all about diffusivity balances. It's momentum diffusivity over thermal diffusivity. And this is a very useful value when we work out these correlations. So, let's think about one other invaluable dimensionless group that we're likely to see. And this is all about advection now. We've talked about convection, heat transfer by external means of removal due to buoyancy. Let's think about advection. And when we talked about advection in the previous part of this lesson, we said, look, imagine a little control volume. It's static, and you've got something flowing through that control volume. It might be a solid, it might be a liquid. And so the advection heat transfer then is the amount of heat transferred from that moving body into my control volume. Okay, so how do we determine whether or not this is important or not? And the answer is, perhaps unsurprisingly, with a non-dimensional group. A non-dimensional group named after Frenchman Jean-Claude Peclet, and we're dealing with the Peclet number here. And the Peclet number, excuse the typo on the board, that should be PE, not RE. The Peclet number is the rate of energy advection divided by the rate of energy conduction. Now let's think about this a little bit carefully. So the rate of energy advection is the amount of energy coming into my control volume as a result of material motion. The rate of energy conduction is the rate of energy transfer within my material. Okay, so if we've got a high Peclet number, that means advection dominates the problem. Which means if we're thinking about the problem from the standpoint of my control volume, the energy is all coming in via that advective process. So conduction is likely to be utterly negligible. This is a key way we can solve advective heat transfer problems. Now, there's another thing here that we can use the Peclet number for, and numericists will already know this, but when we think about writing first principles numerical codes to solve heat transfer or coupled heat transfer and mass transfer problems, then the Peclet number also determines the numerical scheme that we use, because numerical schemes have to take into account which way our dominant information flow is going. And in this case, our dominant information flow is going with the flow. If we include diffusion terms as being equally significant, and we can think of thermal conductivity as a diffusion term, then you actually get quite bad numerical instability. So we're not going to be talking about that directly in the course, but that's another use that we can put the Peclet number to. So let's summarize a few key points. So what we talked about in this part of lesson 6 are non-dimensional groups. Non-dimensional groups are key to understanding problems. We've used them in this case to understand heat transfer problems, but we can use non-dimensional groups everywhere in engineering to get a clear mental picture of what is important and what is not important. So this helps us build our mental model so that we can basically get a good understanding of the problem before we attempt to solve it. So that means when we get to the answer, hopefully it's the answer we expect based on our initial understanding. And if it's not, there's a little bit of thinking to do as to why it's different. So the key non-dimensional groups we looked at as related to heat transfer are the Biot number. It gives information on whether our problem has internal temperature gradients in more than one dimension. We looked at the Nusselt number, and this gives us information, quantitative information, about the magnitude of convective heat transfer coefficients. Nusselt number correlations involve the Reynolds and Prandtl numbers. We also concluded by looking at the Peclet number, which gives us an information about the balance of advective heat transfer to conductive heat transfer, and yet again can be used for problem simplification.